Imagine you want to buy a new laptop. You open a computer magazine and find a thorough test and comparison of several models by an expert. They even gave grades to each laptop to easily gauge their performance and quality. Unfortunately, the one model you're interested in is not included. Is there a way for you to figure out where it would have landed in the test? I'm Bernhard Werner, and this is an introduction to formal concept analysis. In our fictitious computer mag, we might find the following table. Every line represents a laptop model, and in the columns we find various attributes they do or do not have. Let's say whether they have a CD drive, a number pad, an HDMI port, or some form of biometric ID. Whenever a laptop has an attribute, we mark the respective cell with an X, otherwise with nothing. The technical mathematical setup would be the following. A set G of objects we are interested in, a set M of attributes, and a relation I, which is a subset of the direct product of G and M. The triple G, M and I is then called a context. If you are unfamiliar with this notion of a relation, don't worry. For all our intents and purposes, we can and will only work with tables like the ones on the left. The set G of objects in the rows, the set M of attributes in the columns, and little x's, whenever an object has an attribute. One hopefully obvious question one might ask now is which objects have which attributes in common in this context. Let's take the boundary and the cheese book. They share the fact that they both have a CD drive and biometric ID. The other way around, we can ask which objects have exactly those two attributes in common. We already know two of them, and looking at the context we see that the universe also has those attributes. Let's do the step one more time. If you look at all attributes these three objects have in common, we end up with the same two as before. So, if we want to analyze the laptops based on the attributes, we can't really look at the boundary in the cheese book alone. Through the lens of the attributes of this context, they look the same as the universe. Let us try to formalize these observations. For any subset A of our objects, we define A' as a set of all attributes that are common to all elements in A. Similarly, for a subset B of attributes, we define B' as the set of objects that all have all attributes in B. This describes exactly this back and forth we just looked at. We call these the derivations of A and B, respectively. These operators, which turn object sets into attribute sets and vice versa, have plenty of interesting properties. I will only show you some for object sets here. The ones for attributes look identical. Two properties we already saw in the previous example are the following. If A is a set of objects, then first A is a subset of A double prime, and second A prime is the same as A triple prime. This means that going from objects to attributes and back can be seen as a single operation on the objects. But doing it more than once won't give anything new. In math, we call these closure or hull operators. A double prime is the smallest set of objects that looks the same as A when we only consider the respective attribute sets, A' and A triple prime. Another fundamental property of the derivations is this one. If A1 and A2 are sets of objects, such that A1 is contained in A2, then A2' is contained in A1'. The order of sets gets reversed. This makes intuitive sense, I hope. If we are interested in attributes that are common to certain objects, then we get fewer attributes the more objects we are looking at. I won't go through the proofs of these statements here. They aren't too hard, but a bit finicky to write down and not too much fun to watch. But you should definitely try to prove them properly as a homework. With these properties, we can pair up objects and attributes much better. This is realized via a concept called concepts. In our context of laptops, we saw that the boundary, the cheese book, and the universe form a sort of unit together with the attributes they share, having a CD drive and biometric ID. We call this unit a concept. More formally, a concept is a set of objects A and a set of attributes B such that A double prime is A, B double prime is B, and A prime is B. The object set A is then called the extent of the concept and B the intent. What we've seen in the previous section is that we can get all of these concepts by taking any set of objects, let's call it C, and then compute the intent as C prime and the extent as C double prime. If you wanted to write a computer program that actually did that, then there would be more efficient algorithms to find all concepts than looking at all possible sets. But let us not concern ourselves with algorithmic efficiency here. Seeing this definition, you might say, fine. We could define this, I guess, but what is it good for? Absolutely nothing, I would answer, at least not in and of itself. Where it gets interesting, though, is when we consider how concepts are related to each other. If we have two concepts, A1, B1 and A2, B2, it might be the case that A1 is contained in A2. In this case, we say that the first one is a subconcept of the second one, or that it is smaller. And we already saw that this is equivalent to B2 being a subset of B1. With this notion, the set of all concepts form a so-called lattice. That means we can draw the following diagram. For any concept, we draw a little node labeled with the extent on the left and the intent on the right. Whenever one concept is a subconcept of the second one, it has to be lower than that one in the diagram. I took the liberty to abbreviate the laptop names to make it a bit more legible, but it's still quite busy, so pause and take a moment to look at it. We now connect two concepts with a line if they are neighbors. That means if one is a subconcept of the other and no other concept is between them. This concept lattice now tells us just about everything about how different concepts are related. Let's start with the concept we already talked about and which sits here right in the center. It was characterized by the fact that exactly the Boundary, Cheesebook and Universe laptops have the attributes has a CD drive and has a biometric ID. We see that all concepts below it have those attributes too, but more. As a consequence, the extents have to be smaller object sets. The other way around, all concepts further above contain the three laptops we started with, and then some, but fewer and fewer attributes. We can also see that no laptop has all attributes and that no attribute is present in all laptops. This is due to the empty extent at the very bottom and the empty intent at the top, respectively. One last thing I want to show you here. Let's take two different concepts, for example these two. Then there exists a unique third concept that is as small as possible, but bigger than the two given ones. Here it's this one. It is called the supremum, or the join of the given concepts. You can see that its intent is simply the intersection of the given intents. The extent contains all objects of the given extents, but we have to take the double derivation. Because of that, we have more objects here than the three given ones. Similarly, there always exists a concept as big as possible but smaller than both given ones. It's called the infimum, or meat. With these ideas, we could start to look for connections between certain attributes. For example here, every laptop that has an HDMI port and biometric ID must also have a CD drive. Try to see how this directly follows from the concept lattice on screen. Unfortunately, as you might expect, these networks become incredibly complicated when the number of objects and attributes grow. Therefore, we leave them here and continue with a different direction within this theory. Before we do so, however, I want to show you a few entirely different examples of where contexts and concepts are useful. If you would rather continue with the laptop example, jump to this time in the video. A nice example for this process is taxonomy used in biology. If you use a list of all vertebrates as our object set G and a whole bunch of physical properties as the attribute set M, we would find many well-known subgroups. For example, if you start with the attributes has memory glands, has a neocortex, has hair, and has 3 middle ear bones, the associated concept B', B', could then be called mammals, because that are exactly the animals described by these attributes, at least according to Wikipedia. Adding more and more attributes would decrease the number of animals that are described by them, and you would get the orders, families, and genera you are familiar with. One concept would describe cetacea, others would describe fruit bats or wolves. This illustrates that you should really think of a concept as a tangible descriptive category. When we analyze some arbitrary objects and attributes, we won't necessarily find nice short names for each of them though. Now, let's move over to quote-unquote proper math, where we will see that concepts can describe very concrete constructions. The fundamental building blocks of projective geometry are linear spaces, points, lines, planes, etc. To see how they relate to each other, we can build the following context. Let us take all points, lines and planes in 3D space as our objects. Moreover, we use them as our attributes too. We say that an object G has an attribute M if the geometric space G is properly contained in the space M. That means when G is a point, its attributes are all lines and all planes it lies in. If G is a line, the attributes are all planes it lies in. And if G is a plane, it doesn't have any attributes at all. If we take a single point as a set of objects and compute the hull, we get itself. So we have these very basic concepts which describe only a single point, either itself directly as the extent or all lines and planes running through it as the intent. If we now take two such point concepts and compute their join, the intent will consist of all lines and all planes containing both these points. In particular, it will only include a single line, the unique line connecting the 2 points. That means the join of 2 point concepts models the geometric operation of connecting them with a line. Similarly, when we start with a single plane as an attribute, we get concepts representing these planes alone. And then the meat of these plane concepts will have a single line in its extent, the line in which the planes intersect. This idea is so fundamental to the field of projective geometry that we use the words join and meet to refer to the geometric operations of connecting and intersecting, even if we don't think about this whole concept lattice machinery. The last non-laptop example I want to talk about is Galois theory. This is a complex topic that needs several 90-minute lectures to get all its nuances right, but I try to give a 2-minute summary. So this is mostly for the people who are already familiar with these ideas. In Galois theory, we study fields. These are generalized sets of numbers in which you still can add, subtract, multiply and divide by. In particular, the number sets you are probably used to, the rational, real and complex numbers, are all fields. To understand them, we often look at field extensions, i.e. what happens when one field is contained in another. Again, imagine the rational numbers as part of the real numbers as part of the complex numbers. A go-to strategy in mathematics is to analyze something by analyzing its behavior under certain functions. For fields, these functions are called automorphisms. They need to have certain properties which I don't want to get into here. With these special functions, we can now build a context. For a suitable field extension, like from the real to the complex numbers, we can take all the numbers in the bigger field as our objects. And we use all automorphisms of the bigger field as the set of attributes. We say that an object G has an attribute M if the number G is mapped to itself by the function M. With this, the extent of any concept will be a field that sits in between the ones we started with, and the intent is its so-called Galois group, the functions that fix that particular field, but not the bigger one we started with. With this connection of numbers and transformations of numbers, Galois theory can prove results such as there is no closed form for the roots of polynomials of degree 5 or higher. When discussing the derivations of a context in a generalized setting, they are often called Galois connections, because their behavior was first studied in the form of Galois theory. And this, I think, is enough of serious math. Let's go back to our laptops. Looking at our laptop context again, you might have already noticed that we didn't include properties which are usually more relevant when buying a computer. Not the price, not the clock speed or RAM, and not the screen size. The problem is that they are given by numerical values and can't be directly classified as present or not present in an object. Let's start with the screen size to see what's going on here. If we added the screen size to our data table, it might look like this. Because the entries aren't just yes and no, this is now called a multivalued context. To work with it, we have to transform it into an ordinary context. This process is called scaling. It's essential when doing data analysis because this step is where we model how properties are interpreted. For screen size, the step is quite simple. Instead of using one attribute with multiple values, we use one attribute for each possible outcome. Then we mark where each laptop fits in these 3 attributes. Let's look at the price next. Using every possible price as an attribute is a bit overkill, of course, but even using just the prices that appear here in this context as new attributes won't be that useful. Firstly, because any new laptop we might add later on would probably not have a price we see here. Secondly, it wouldn't be useful as the particular prices aren't that interesting. We mostly care about the ballpark the prices lie in. We can resolve that by using bins, say ranges of 500 euros. Then we can mark where every laptop lies in. But we can do even more. When looking for a laptop to buy, cheaper is better. Therefore, it might be more useful to mark whether a given price falls below a certain threshold. In particular, whenever a laptop falls into one of those less than categories, it must also lie in the higher ones. For example, the tin book costs less than 1,500 euros, so it obviously also costs less than 2,000 euros. This way, our subsequent analysis will have this notion of lower prices being better built in. Moreover, it's now easy to see that the cheese book costs more than 2,500 euros. Depending on what you want to know, it might even be a good idea to include both cheaper than and more expensive than categories. But here we'll stick with just the former one. We could have done something similar for the screen size too, but it isn't obvious whether smaller or larger screens are better. That depends a lot on your work mode and preferences, so we keep this neutral scale here. Now let's quickly add GPU memory and clock speed. For both, bigger numbers are better. Let's use one attribute for the GPU, whether its memory is at least 16 GB or not. And for the clock speed, we'll use two bins, at least 2.1 GHz and at least 2.8 GHz. There are a few more standard ways to scale a multivalued context. But for numerical data like we have here, where either smaller or larger numbers are clearly better, this basically is it. To finish this section off, let's go back to the premise of the video. We assume that this table comes from a review by an expert, and they also gave each laptop a grade based on their professional but subjective assessment. Something like this, where A is best and E is worst. Let's defer scaling this attribute until later though. To finally use all this data to make an informed decision about buying a laptop, we need to know how different attributes necessitate one another. Earlier, I asked you to look at the concept lattice of our then still smaller context and verify that every object that has an HDMI port and biometric ID must also have a CD drive. We call such a statement an implication. Let's formalize its definition. For two attribute sets, B1 and B2, we say that B1 implies B2 if every object that has all attributes in B1 also has all attributes in B2. In other words, B1 prime must be a subset of B2 prime. We use this double right arrow to denote implications. Let's look at some easy to prove properties of implications. First, if B1 contains B2, then B1 always implies B2. That's because we already saw that the derivations reverse the order, so we get B1 prime in B2 prime immediately. Because of this property, we are often only interested in implications where the left-hand side and right-hand side have no attributes in common. Another thing to note is that any attribute set B implies B double prime. Again, this is just a reformulation of one of our basic facts about derivations from earlier. B prime is the same as B triple prime and therefore a subset of B triple prime. A last property for now. Given B1 implies B2 and B2 implies B3, we also get that B1 implies B3. Overall, we can say the notion of implications used here in this formal sense behaves as you would expect from something called implication. In particular, these and other rules allow us to derive some implications from others. As a result, we can look at a relatively small set of implications from which we can generate all others. This small set of implications is called a basis. It encodes all information about the relations between our attributes. I won't explain here how such an implication basis looks like or how we can compute it. The important part is that there exist algorithms to find them. And with that, we can finally tackle the task from the beginning of the video. Assume that this context is the data we got from our computer magazine. It's the same as before, but with more objects. We are now interested in an additional laptop, this Enterprise here, which wasn't part of the test. But we would like to know how it compares to the others. Our best guess is to take the given attributes and see how they relate to the grades at the end. Let's keep things simple and say a good laptop is one with a grade A or B. So we scale the last attribute like this. Now we want to find implications such that the attribute is good appears on the right hand side, i.e. we wish to know properties good laptops have. One such implication looks like this. Any laptop with a CD drive, number pad, HDMI port, biometric ID, a 15-inch screen, less than 2,000 euros, more than 16 GB of RAM, and more than 2.8 GHz is good. But this combination of attributes characterizes exactly one of the objects in our context, the workbench. It is very unlikely that any additional object we want to classify fits these criteria. What we want is a so-called minimal implication, one where we can't remove any attribute on the left-hand side without losing the attribute we want, being good, on the right. In other words, a minimal implication describes the maximal number of objects for which this implication holds. Here in this context, there's only one minimal implication, and it looks like this. Any laptop that has a CD drive, biometric ID, costs less than 2,000 euros, has at least 60 GB of RAM, and at least 2.8 GHz is good. The reason why this is minimal and why it is the only one are the same in this case. All good laptops in our context fulfill this combination. And comparing the enterprise with this rule, we can at last say that it is good. If you want a good laptop, it seems fine to buy this one, at least in this context. This was just a small glimpse into formal concept analysis. As we've briefly seen in the middle of the video, it can be used in various disciplines and areas, and therefore there are numerous special cases and variants. In general, it is often used to describe inherent structures, to visualize these structures via lattices, and to analyze data. In my PhD thesis, for example, I used it in a way very similar to what I've presented here to create a handwriting recognition algorithm. Depending on what you might want to use it for, there are many ways in which you can continue with this, but the original work on this by Bernhard Ganter and Rudolf Wille is a good place to start if you're interested in. Link down below. And with that, thank you for watching and until next time.